All right, afternoon. Thanks everybody for joining in this week. We have, I think it's going to be a really interesting talk this week from Cissie Mei from Jefferson Lab, and she's going to be talking about millisecond network monitoring on Linux. And as you can see, this is representing a paper that was accepted at the Indus workshop at SC25 this year. So I'll turn it over to Cissie to get us started.
Oh, thank you. Thank you for Jason to invite me here. As Jason introduced, I'm from Jefferson Lab. I joined it's almost 4 years now. So I first worked data surrogate models related to machine learning, and then I started to work for Ilya boarding on the EJFAT project and get in touch with the networking field. And this is a project that covered by JLab LDRD that I started to lead in fiscal year 24, and it's in the second year. So yeah, with this given, I think I will just start to talk about this eCounter. I'm not going to throw every as an academic presentation, but more like engineering slide. But before the demo, I can just quickly walk through what is this eCounter and how what is the architecture looks like. So this I call it eCounter, and the full name is like inline per IP network monitoring and millisecond resolution via eBPF. I think this is motivated like years ago. So people ask when I was doing, when I was like ops engineer at NVIDIA. So I was in charge of the dashboard, Selene, that is 400 node cluster with more than as a 500 node cluster with more than 4,000 GPUs, and we do see that when it goes to network, because people, if there's an incident happen, people will ask, okay, what is our network speed? It looks like a moment ago. Then I go back to see the network speed is always lower than we assumed. So this is what yeah, what I put into this this slide that if we deploy something like a promiscuous load exporter or other network and promiscuous, not this exporter but other related HTTP based exporters, the moment the peak you see is always lower than that because those scrape interval is just this HTTP script based exporter, the script interval is just like tens of seconds or even longer than that, or maybe at a minute level. So you will miss many of the peak values. And I think I have go through is that the node exporter is based on some counters at proc, NetDEV discounters, and you can also use some other commands to check them. But it's basically L2, level two information like how many bytes packets and something like this looks like this, and then it goes to, and then this node exporter will put those information into a web page, and then you'll have your centralized permission server to periodically scrape from them and transfer into string, and then your Grafana dashboard and then just pass those numbers and deploy and display them as graphics. So this is a real experiment I have done on JLab testbed that I set up a cron job. I have a sudo on that node, so I was allowed to do that. I set up a cron job and I use an activate an Apple session that is sending data at 8 Gbps for 60 seconds. And then need to sleep for another 1 minute and then activate again. So if the dashboard is accurate or fast enough to catch that, what we see in the dashboard is actually should be 8.16. And you see, but you will find this dashboard. This is a one day record. Is that it's always for below. If it's always low, it's always lower than that value, and sometimes it just got offline, and that is happening every day as ops engineer. We will see. So this I think this is a background that tells that the wide node exporter or HTTP-based scraper cannot catch up the real traffic. So then I think it's 2022, I read this paper called MilliSampler. Is a paper called a microscopic view of burst buffer contention loss in data centers. Basically, it's developed and written by meta engineers, and they are using eBPF based tool called MilliSampler to measure the traffic at the meta data center at a very large scale. So the sampling interval according to them can like as low as small as like 10 milliseconds, and the measures are collected by per CPU core, and then they actually run that for 9,000 racks and run for 4 days. So I think, okay, this is really good, but why? And unfortunately, this is just activated. I think every 2 minutes per hour, and then okay. So then I ask myself, so this is too good, but why cannot run continuously in a data center? So I guess the reason. I think there are many reasons. First, Meta's data center is like a more HTTP based, so there are many short-lived sessions, and which if we run continuously, we are not able to port everything in this eBPF kernel out. This is the main reason. And I think now let's go to what is eBPF. Basically, eBPF is called Extended Berkeley Packet Filter. The name suggests it's very suitable to do networking stuff. So and it's invented by Berkeley, I guess. And it is something in the Linux kernel, and it's really fast. So the way to program with this eBPF, and there are big community on that. There's the eBPF community on that. But for networking, is that it reads every packet that goes to this kernel, or goes through this kernel, and it will read every layer of the headers. So then we then we just filter them based on some rules we define. So now my eCounter goes at this L3 layer because I care about IP to IP, so the source IP to destination IP. And I think the meta one, that is flow based. It's flow based HTTP, and then so this is the program mechanism, and then so the eBPF, when you write those programs, you run them, it's called a hook. So hook is something like you attached to the existing Linux kernel. So you have several places to attach them. One is this is a HTTP hook, and you can attach them before even a packet SKB buffer is created or after TC. So this the XDP and the TC are actually is kind of two types of eBPF hooks. but this some limitation about the XDP hook is definitely faster, but when I run it on our testbed, I found that this XDP hook has 3 modes. So the offload mode that is not supported by InfiniBand, the NVIDIA company, and then there is the normal mode. We'll call it normal mode, but it's another terminology. So what we expect is that has a restriction that your MTU size has to be smaller than 3,3496. I think it's that number. But when we do data streaming with EJFAT, we usually use jumbo MTU size like 9,000. So that's why we cannot run XDP hook, and instead I use the final implementation is prefers this TC hook. When TC hook is more general, and the third type of XDP hook is the emulator of the TC hook. So this go then I guess then this is just a small comparison, and the MilliSampler because it's perfect. It focus on this level 4, and it can tells more metrics, and the I think the user space consumption is just so the user space is just cannot catch up with so much data, so it's not a continuous monitoring solution. Even now, I think maybe it's not continuous. And then the node exporter, firstly, it cannot give you any L3 or L4 information, and so the resolution will be second to million layer. So basically, my eCounter is simple. Is that I sit in the middle. I care about two full metrics. It's full metrics is TCP bytes, TCP packets, number of TCP packets, and then UDP bytes, UDP packets. And I use the map, different maps. The eBPF map is a structure that your user space can communicate with your kernel. So this is what is our eCounter is that E9 per packet, so L3, which means per IP address, and millisecond resolution network monitoring agent. And I think it can run concurrently with scientific data acquisition system that EJFAT or Ethernet is in many of the use cases of the Ethernet. So this is the implementation of the eCounter, that the kernel. So you have two parts. The kernel part is a map. So this map is just a map. Even it is not it is a hash table, but it's because I use it as a hash table. But even it's an array, it is also called a map. It's something eBPF defines. So it's not the general map we are talking about in data structure. So I'm using the eBPF, the map structure of eBPF map. And so we have key like the IP and the protocol, and then we have values, the packets and bytes. And this is the map that the map type here, this capital BPF underscore map is the eBPF map structure I'm using. So this size is 48 kilobytes, and when I attach that hook, I would receive a message that I use this memory lock size, and in comparison, this is the CPU L1 size for all the cores aggregated by all cores compared to that map size. And on the right side is the architecture of that eCounter. So basically, we have two main parts. So the kernel part is the implementation of the TC ingress hook, TC egress hook, and the XDP ingress hook. So you can attach three kinds of those hooks, and this user space. And you attach those hooks, and afterwards you pin them into some memory, and then my user space will give the parameter of the map pin space to the user space, and it will periodically read from the map and transfer data. So the real thing in the kernel is very, very small. It's just for this structure is some counters. So what I do in the user space is more heavy. Is that I have two workers. One is a fast worker, and it is activated at a fine-grained time tick. Now it's like I can activate like every 1 millisecond, and like 50 to 50 seconds, but at every fine-grained time tick, I will take a snapshot of this kernel counters, and this snapshot, and in 1 second of coarse grain period, you will see those is keep continuous growing, and then I will at the end or at the beginning of every coarse grain tick, I have another worker that try to export everything into the more user-friendly format. And now it's like I transfer them into an array. I didn't save the timestamp of those fine-grained ticks, but just the values of the fine-grained time ticks. So I have a ring buffer here that only saves like next 2 minutes of the records. So this is a snapshot of worker. So it's worker 1 is just to take a snapshot, and the worker 2 is get a diff of those snapshot and export them into the bin into the time series. So music, then we go. Yeah, I have then it talks about the validation. So I think I have tried everything I can to validate this. So first I compared with those tools they called NC as netstat that I triggered the traffic one by one, the packets one by one, and see if my counter is increased. The kernel space counter is increased one by one. And also I generate a lot of traffic and compare the counters because I know where the source and destination are. So I actually know that the increase of those statics is coming from which pair. So this is a kernel I have go through. I think I've tested with iProof 3 and also the packet generator to generate a fixed amount of packets like 1 million packets and see if the packet number is increased by 1 million. And the user space so the user space is harder than kernel space because I wanted to achieve this continuous monitoring goal. So for like for the fine grained time tick, there is like I can activate 20 times a second or 40 times or 4,000 times per second. But actually, when you want to activate them for 4,000 times per second, you cannot achieve that number. You only achieve like 80% of the beans, 80% of the beans. And hmm, and then I just run the iPerf streaming and I can configure the payload size and I can configure the target rate. So I think and I get my output into Python and calculate okay what is the per second Gbps they achieved, and it gives me 8.16. Actually, this is the thing that the iPerf is just calculating the payload size, and the payload size, not the header. But my eCounter will also account those header size, so that's the extra, and it is exactly matched what the header, the UDP header is 28 bytes extra. So that was why we see 2% more. And I have tested them Ubuntu system, my system, and the ARM node, and also I used a DPU. DPU is the bottom is connected 662. So, but yeah, the system works on DPU as well, and the multiple MTU sizes. So and also then I try to the other question is that if I run this continuously, will I slow down? Will I slow down my iPerf session? So I have done I have run in the eBPF hooks, three eBPF hooks, and try to measure achieve the iPerf performance without the hooks. And the thing is that the throughput is just within 1% difference. And it's hard to say what this one difference comes from because we know that the network speed is just fluctuating. And then measure the how much resources we utilize. So for the target, I mean for the target is 4,000 beans in 1 second, but we got 3,200, and then you see the maximum CPU utilization, and it's only 4%. And the chip per second, this JSON report is only one pair, but even even its more pairs is still not that big, and those are older. Those are older. Those numbers utilization or measured with PID stat. So basically is that if you want your throughput, you don't want if you this is some balance, the design balance that you are always facing in the programming. That if you want your high throughput, then you cannot expect a low utilization. So, and then on the left is what I run. Those are different runs, not the same traffic pattern, but you do see when I target and then different calling frequencies, you see we see much network traffic much clearer. And even for this one, it's extremely, I think we got more than 3,000 per second samples. And you do see this up and down, I think it's a cache miss. Yeah, for this thing, I think it's a cache miss or hit difference. But for this spike, it's definitely something network itself. So I do, at the time when I submit the paper, I don't have two homogeneous nodes for the stress testing. So I got a very slow ARM node and a faster AMD node. But then after I submit the paper, I do got two nodes, the two homogeneous nodes to test them. So I do say if I run them this is the sender and this is the receiver. There's only one hop of switch. They belong to one rack, and then this is all and they are all connected to the top of rack switch. And those two nodes are like a 100 Gbps links, and it's only single link. So I have attached the egress hook sender into a I have attached the egress hook to the sender and attached the ingress hook to the receiver, and I use 16 parallel streams and to measure them based on 5-round average. So you see that there's almost no influence on how much the throughput we can achieve. So basically, the eBPF is touch the kernel, so it's through very well. So then I just got two nodes to test those at the current stage. So I cannot perform these experiments at scale. But I do a theoretical analysis is that that's because this eCounter has two parts. One is kernel, one is user space. So the kernel part is that it is updated based on every packet arrives. So that is proportional to the maximum PPS. So it's the packet rate. So this is a feature that is limited by NIC or CPU. Basically, it's a factor of how good our network card and the CPU are. And so this thing is not related to the user space, but the user space is more complicated, as I deeply feel that so it is I think this is the frequency is the frequency sorry frequency is the thing I denoted that the number of fine grained beams in a coarse grained window. It doesn't have to be 20. It doesn't have to be the 20 or 1,000 or something. It's just a number, the frequency, and L is the number of active connections in a coarse grained window. In here, it is 1 second. Sorry. So now for L equal to 1, I have pushed this FL to almost 4,000. So unlike the meta system, and we have a lot of short-lived sessions, I assume the SciDAQ environment, such as SciDAQ environment such as EJFAT. So we will get a high data rate from single race source, and then we will not see that the server just come and go and say, oh, just send short-lived sessions. I assume that. So based on this use case, I think the AL should be within tens that within a coarse grained window. Now it's 1 second. Actually, we can just make it a 0.1 second or something. We can always get it like the L is tens. So even and then another thing is that if we get if we deploy it more distributedly, there will be more cache misses. Like now we only got one pair, so it's a hard pass. But then if I have more, then maybe we'll hit a cache. We'll see more cache misses, and then the update is just slower. So if taking that into account, and then let's say we target at this the product of FL to 1,000, and we still have a lot of room. So I think the continuous monitoring is possible here. So to summarize, this is the thing I'm working on. It's a lightweight millisecond resolution, and it's at the L3 level. and it almost has no influence based on our 100 Gbps experiment. There's almost no experience and very minimal influence to the CPU and memory utilization. And this eBPF stuff is not tied to any application thing. You don't have to say, okay, I run a PF and that goes to eCounter. It's attached to a NIC network interface, which we can see through the IP command. And it is works on or modern Linux platforms. Actually, the code was firstly implemented on my old Linux laptop. It is a kernel 4.18, and I make that work on my laptop first with a Wi-Fi network interface first, and then I goes to the test bed in JLab to test it on higher data rates and more newer generations. Now let's talk about the downside, and this is the thing I want to solve. Try to solve in the future. So we case that the user space is code is always much slower than the kernel space. And when I do the aggregate, when the fine-grained time typically arrive, when I do aggregate, that costs a long time. So you do see that when you check those fine-grained bins, the first bin there is much higher value, and this is more serious for if you push the fine-grained, push the temporary solution higher. And because this is the TC, the traffic control is all, it has to be, it stays in the Linux kernel, so it cannot watch the things for InfiniBand or any kernel bypassing stuff. And to see the deployment difficulties that sudo, you have to sudo everywhere, and this causes me that I can only get a very limited testbed resources to test them, and you basically. I don't think this is a Docker one-click thing, because now for many other network monitoring tools, it just pour some Docker images and it just deploy some Docker command and it's there. But I don't think that our eCounter cannot be used can be deployed in that way. Up to now, I have never tested them with a virtual machine or a Docker image. But yeah, I have never tried them. So let's look at in the future. So I think when I write this paper, I read a few papers from Ethernet about high touch and how you use P4 to get per packet visibility. But that's basically on the L2 and L3 switches and the routers. So maybe this eCounter can be a counterpart of the high touch service that give you host side per packet visibility. And the second in this is eCenter is what I'm at the second year I'm trying to work on this LDRD is that I want to build some kind of visualization tool to see what the traffic looks like at real time in a rack level or smaller scale. And then if we can get this very time series, the third direction I was thinking that okay, if we can get a very fine-grained time series of network traffic, and how do we combine this AI like to do auto anomaly pattern detection and see if we can like detect some anomalies. And even more aggressive, maybe if the pattern is good enough, then we may just use those telemetry-based feedback to control to feed back into the control loop of that SciDAQ experiment and to real-time steering the experiments. So this is the acknowledgement. This is, as I said, it's a JLab LDRD project, and thank you for JLab to give me this grant. And this is the first project I've ever led. And the first year we have 3 persons work on this project and on different aspects. And so I will stop here if anyone wants to discuss this eBPF map performance, but then I will just stop here. And why I use this kind of eBPF map is not based on say, okay, there is a eBPF map, look, I will use it. It's based on some survey reading that it's based on some paper reading that tells give me some assumption what that performance would look like, and then and then I do it, and I pick the one the pick one I think is good, suitable for my goal and current now. So yeah, I think this is the slides part, and I will go to the demo part. But if there is any question, please ask, and then you answer after I answer question, I can go to the demo part. Is that okay?
Yeah, if anybody has any questions, please just identify yourself. Let's see,
So
oops, hold on, let me make sure everybody can unmute themselves.
then I think there's no questions. So I will go to the code part. Mm, let me see. Sorry. So I got a GitHub here. So everything is under this JLab DPU telemetry eBPF. What I'm going to show is the same. Is the same with this Jefferson Lab to be the repo, and yeah, the README and the works and the steps to how to compile the program and how you attach those hooks are just given in the README. So I think today's demo is like I started with I already got the I already got the kernel part work in the kernel part and the user space part compiled and attached. So here I have like this, if I look at the code, they have kernel egress TCs, and then kernel, everything starts with the kernel is a kernel part, and they will compile to kernel, kernel.o, and that will be attached to the corresponding hook spaces, places, and then there's a user space. This is the user space, the TC dash hood user space that can read anything. Although it's started with TC, but it can also read XDP hook maps. So it works for either direction and works for either XDP or TC map. So I already started something a moment ago that I compiled those the hooks and attached ingress hook, the kernel ingress TC to this node. This is the receiver. And then I run those commands, the TC, and I run this sudo TC, and then this is the target frequency. Now it's like 20 samples per second, and then I ping this my eBPF map to this location, and then you will see it will give you some mappings, and then when some traffic comes, they will activate this. Because my code has some zero suspicion. So if you don't generate, if there's no traffic, it's just stay here, stay still as is. Let me see. So I think this is now it's very quiet. I'm trying to shut it a little bit. So now it has no traffic coming, so it stays still. Now what I'm doing is that I have a EJFAT. I have a fetch 6. So I go to go here. Okay, so and these are two nodes at the JLab EJFAT testbed, and we have. So for each of them, we have a high-speed network and a low-speed network. So this high-speed network 2 here is our 100 Gbps NIC. Its IP address is 0.4, and the other one is 0.5. 0.6 is EJFAT 5 and EJFAT 6. So basically, I start a iPerf listener, iPerf server here is a listener, is a traffic receiver here. And then I will do this one is EJFAT five is will be sender. I will activate iPerf session. That dash B is so that this dash B is the IP address we are going to bind. So we are going to bind this high-speed network address, and then we are going to activate 16 sessions, and we are going to use UDP traffic, and we are going to unlimited. This is a dash B0 is at the unlimited bit rate, and this is activated for 6 seconds. So when I activate this, we immediately see this is generating some traffic here, and these are some network order integers. So those are the four being the four time series is traffic to connect them. So I personally I do not have a long experience of programming with network, so I do see some interesting things when I program this iPerf 3. The iPerf 3 is UDP, and I actually see there was a TCP traffic generated at the beginning, and because we want to report those data rate, and they're actually activating TCP traffic. So this is something I didn't expect it, but I did find to use this I did find out with this tool. So So this is the user space, what we are going to, it looks like this. But when we go to the kernel space, you don't have to use a user space to read the kernel space data. You can use command line tools. So this is the eBPF map. So eBPF sudo map show. So we'll this is the command interface that you are going to work with your eBPF kernel. So when I do this eBPF tool map show, you do see this eBPF LRU hash is the type I asked, and this is the map ID. The map ID is 13, and the map name is this. So actually, I can use the command line to query those. Yeah, so I can use the command line like a dump this map content. So if you see this is one pair, this is a TCP traffic, and then this is a value, and this is UDP traffic, and this is a value. And this IP is just network order integer of that IP address. And I do have some like help me. I do have some helpers to let me see, and yeah, I do have some end to edge convert, and then if you want to this one, so it will show me what is the network looks like. Is exactly the IP address we are working on the EJFAT test bed now. Yeah, yeah, this is the real-time demo part. So any questions?
All right, thank you so much for going through that, Cissie. If anybody does have questions, you're unmuted. You can.
If that is not, if we have no questions, then I'm going to move forward to the third part. Is that to the third part of this is how to improve this. I do see a question. I do see a question there about timestamp thing. I think that depends on what you write into your code. If your code, your eBPF map does not record, does not so here the eBPF map structure, there's no entry for the timestamp. So then you will not get a timestamp of each packet arrive time. But if you wanted to, then you have to do something in your map to explicitly require that you want to record the arrival time of each packet or whatever. You have to implement with the code. It is possible, but you will get extra cost for that. You will get extra cost latency for that. And I do not have the JSON the timestamp in my JSON record now. The fine grained beans just lost the timestamp of the timestamp of this is lost. But we do have coarse grained beans outside that the first level key is the timestamp in epoch the second since epoch time. So if then I will move on to the I will move on to this eBPF map structures. So for now, so for when I first implemented the first version, what you see here, I know that a eBPF map will be something that definitely will work because our colleague who is retired in Jefferson Lab, he had did something in array, and I know that's going to he did something programming with the BPF map type per CPU array, and that is work. So I know this eBPF map thing will definitely going to work, but now when I was programming that, when I was programming, I was brainstorming with my AI, and my AI said, "Okay, you are going to stream that, and that will reduce your user space cost." I was, "Oh, dear, does that really? That's really have the kernel streaming? Yeah, that's true. We do have eBPF kernel streaming, but it's not supported. Basically, I cannot test on my laptop because my laptop is a kernel 4, and this is a kernel. And you have your you need your Linux system to be newer than this and to implement this. This basically is a ring buffer structure that the ring buffer structure and I will look into that and see if I can improve that because I want to reduce those first beam spike thing. So I can talk about more about this first beam spike. I try to solve that. First, the user space just a single thread program, and then because I want to reduce the first time spike, okay, I will start 2 threads, and one thread is just doing those worker and export, and then I at every time I launched a separate thread to manage to export those snapshots into arrays and wish that I can reduce the cost. Actually, it does not help. The cost of launching an additional array is larger than the original single thread implementation. So now it's the now I got yeah, that problem is not solved, but I think if the fine grain time tick is that I have 20 samples per second, that spike is not obvious. But if you want 1,000, then maybe it's the thing, and then maybe if it cannot be solved by the user space program, it has to be solved by the AI or whatever afterward to processing to use an estimate. To say, okay, we just ignore the first spike or use some specific mathematics related to get how much percent or whatever. That's a recovery to some value that is not given by this program. Then, and I also this is the thing I'm looking into that as my personal interest, and I will look into how to upgrade if this kernel streaming will help. It may not help because we may lose the map structure, we may lose the key value as we wanted. But yeah, I will see and measure it. And another thing I'm going to show is I have the second year at DRD. I do have some professor at William Mary who's doing some visualization work and very good at web application and help me to implement a view go to repos and then let's see, search last. Let me go to on this one. Okay. So give me a few seconds. I will try to search them out. I will have the show and yeah, here I do have LDRDVs here. That yeah, this is something I want to ask you as a network engineering community. And I do think this is something valuable that that is that we can continue in this direction. Because actually, as I said, I do not have much rich experience in network at all. So so someone yeah, some professor help me implement this view. What we want to do is that assume this is a rack, and at the second level, I want to see who is talking with who, and the color the color is the total bytes, indicates what total bytes. So if it's darker, means when there's not traffic generated, and if it's lighter, then there's fewer. So this is a very artificial data. It's basically random generated by some seed and the front end. But we are next as a next step, we are going to connect them with the real Redis database, which will this Redis database will be connected with many much better network this eCounter workers that the JSON record will be sent to real time. Will be written into this Redis database, and so every client at 1 second will write to this Redis database with the aggregate with the total bytes and the 4 time series bins or arrays. And what we get is that an overview of this rack view of this traffic and the total bytes traffic. And then if we click the link, we will see the sub-second view of the real-time traffic. So I also want to know this community is the feedback from this community. That do you think this is a valuable direction that we can continue to work on?
I did
yeah,
unmute
I think this is
everybody.
all for today. I'm open to questions, and I will stop sharing.
All right, well, thank you so much, Cissie. I did unmute everybody. If anybody does have any questions that they want to ask, or you can, of course, use the chat room.
Any questions?
No, I don't see anybody asking anything, but we can wait for a minute. So I do have a question. Is this something that is available for people to sort of download from your GitHub right now and install, or does it require a lot of additional configuration by you or your team to sort of get working?
Okay.
Can people hear me? I'm not sure if people are hearing me.
We hear you, Jason.
Yeah.
Okay. Cissie, are you able to hear us?
Thank you. So I think is that all for today, Jason? Or we should wait longer for questions?
So Cissie, are you able to hear us or no? I think maybe her audio is not working.
No, I cannot. Yeah, I cannot hear anybody. Sorry.
Oh, okay. Well, that would explain why she can't hear us. Uh,
Can you say that again?
can you hear us yet, Sissy?
Yeah. I can hear you now.
Okay. I was asking, is this something that the community can download from your GitHub right now, so that they can test it out at home, or is
Yes,
it? It is.
yes. It's at Jefferson, the rep, that Jefferson Lab GitHub is open. It's open to the open resource. It's open to the public to download. Yeah, it may be complicated to pin, compile, and pin those eBPF maps, but once that's done, I think it works with every Linux system, and newer Linux system, and every network interface, not only the high-speed one, also the Wi-Fi ones.
Okay. Well, if you are able to send me a link, I'll make sure that it gets put into the email that I send to everybody afterwards. Does anybody else have any other questions? Okay. Well, thank you very much for going through that. If you don't mind sending me a copy of your slides as well, I'll make sure that those get posted along with the video.
Okay, thank you.
All right. Well, thanks everybody for joining this week. We will have the Perf Sonar development team next week giving their usual office hours. So if anybody does have Perf Sonar questions, certainly come to the meeting next week. We'll talk to everybody soon. Hope you all have a good weekend.